To another interesting paper in deep learning, and that is StarGAN, Star Generative Adversarial Network. I believe we discussed sometimes about the generative adversarial network. We may want to look into our channel for that. So this is Unified Generative Adversarial Networks for multi-domain image-to-image translation. Let me quickly try to break down what this work is all about, looking at the title of the paper. And the first is Generative Adversarial Network, which is a technique of having two networks. One is called the generator, the other is called the discriminator. The generator is meant to generate images, synthesize images, and that is as close as being real, so that you can fool the discriminator. And the work of the discriminator network is to take in the generated images and the real images and be able to classify the real as real and the fake as fake. Now we're talking in this paper in a multi-domain image-to-image translation, and the concept of domain in this work is referring to, for instance, if we say a data set that contains all faces of females, that is a domain. If you have another data set that contains all faces of male, that is another domain. So that makes two domains. So it's possible to have a single data set that has more than one domains, as is exhibited in this work. For instance, this here that you're seeing represent one data set, and this represent another data set. So this is the same data set for celebrity. This is from celeb A data set, and in that data set you have multiple domains. You have domains of images that has blonde hair. You have another domain of the attribute of those that have either male or female. You have another a mix of the age, and you have another attribute of the mix of the pale skin. So in the another data set here, which is the array FD, you have multiple domains. One domain will be the set of those faces that are angry, a set of those that are happy, set of those that are fearful. So that's what is being referred to multi-domain. So essentially what we're trying to do is at test time, you want to be able to feed in a particular image and ask the network to produce that same image in another domain. For instance, you may want to feed in a face of a man, a male face, and you ask the network to produce the same face as female. Or you may want to put in a face of somebody that is angry and ask the network to reproduce the same face with the person smiling. That is, how will the person look if the person is smiling. You can also feed in a face of somebody that is young, maybe less than 20s, and you ask the network to produce an image of the same person when the person is 90. That is, trying to predict how the person will look like when the person is 90. So that is essentially what the multi-domain is talking about. So let's now go deep into it and see some of the illustrations. Yeah, in this place, figure 1 is showing the multi-domain image-to-image translation results on the celib A dataset. And what is happening here is that they have trained a network on this dataset RAFD. So they trained a network on the RAFD dataset, which consists of expressions of anger, happy, fearful. So at test time, they now use that network that was trained on this dataset. They feed in samples from another dataset, that is celibate A, and they now want the so they now want the network to be able to now transfer the knowledge that have been learned from one data set into the other data set. Okay, so for instance, you look in this place here, it said you have the input images. So you have this person and you want to produce the same person with blonde hair, the same person with a gender impacted, the same person when it's aged, the same person when it is pale skin. And here you input an image of someone and you want to produce the same person when he's angry, the same person when he's happy, and the same person when he's fearful. And you can see a lot of interesting things here. So one thing you see here is that the images are generated by a single generator network, and facial expressions are labeled such as angry, happy, and fearful. They are from RAFD and not from celibate A, as you can see. So they train the network on RAFD dataset, and they now use celibate A to test if the network could transform the images in celibate A to the same domain, to samples in RAFD. Okay, so that's essentially what this work about. It's about multiple work I've been looking into peer transformation, that is from one domain to another domain. But this work is looking at multi-domain transformation. Alright, so let's see the cross domain, and this is the StarGAN. Now, in comparison of the StarGAN with the previous work, what this is saying is if you have domain 1 and you want to convert them to domain 2, the target, you have to train a generator that will convert domain 1 to domain 2. And if you want to convert domain 2 to domain 1, you have to train another generator that will learn the mapping of domain 2 to domain 1. So that's why you have this key to it. And similar thing for the other ones too. So for you to be able to do transformation between two domains, you essentially will need one generator for each of the domains. But in a StarGAN, you just need only one generator, and by just specifying which is the input domain and what output domain you want, you can quickly see the generator generating for you what you need. So StarGAN is capable of learning mappings among multiple domains using a single generator. we're going to look at a more important thing. Now this is in order to compare the work with the baselines, they decided to show in figure 3 here how the StarGAN works for two domains, just for two domains. So in the A part, you have the discriminator, and what it does is that it tries to take in go to read image and take image here, and we classify the read image as real and fake image as fake. So if the image is real, its objective is to classify it as real, and if it is fake, it's to classify it as fake. And one other thing is, if the image is classified as real, it's also going to classify it to its corresponding domain. Now don't forget what we mean by domain. So if you supply a real image of somebody that is actually laughing here, so we expect the discriminator to be able to classify that image as real and to put the domain that this person is happy. So that's what is happening here. Now in the B part, the generator takes in the input image and the target domain label. For instance, what they did is they put a label, one-hot encoding for each of the multiple domains. So let's say you have 5 domains. So you are going to represent and then by a vector. So whichever domain that you are interested in, you turn it to 1, while the others will remain as 0. So what G takes in both the input image and the target domain label, and its task is to generate a fake image that we can feed into the discriminator to fool the discriminator. So that's what is happening. So we generate a fake image and it goes into the discriminator, and the discriminator will try to classify it as either real or fake. And if the discriminator is able to get that it is real, it will also try to predict the domain of that image. Now, in addition, the generator, while trying to train this network, after generating the fake image, then we will supply it with the original domain label. So here you have the input image and you have the target domain. We want the generator to generate an image in a particular target. Maybe we want it to generate a sad face. We give it a face and we give it a label of that indicates a 1 in the position of the vector of a sad face. Then when it generates a fake image, we now actually feed in the information of the original domain of the input image, which is maybe it is happy. So, and we feed it back into the generator and to reconstruct back the image. And this is how the autoencoder are working for. So that is that. Yeah, so we have the rest are the loss functions that are used. You have a composite objective, the loss function for the discriminator, and that of the generator. So we have the domain classification loss for the real and for the fake. and you also have the reconstruction loss. Then the full objective loss, G, is the adversarial loss, if you look at up here, this one. Then the domain classification loss, which is that of the view, that of the fit, and the reconstruction loss. So that's what you have here. So for the discriminator, we have S, and for the generator, we have this loss. Each of the network has its own loss function defined. You can see that the adversarial loss is common to both of them. Okay? And then you have some regularization parameters to control impedance. So that's essentially what is happening. Now this is the one-hot vector that was used, this representation, where you actually put 1 or 0, where it corresponds to the desired attribute. So the rest are just demonstrations. So here they compare with other baselines. So what it is like, there's StarGAN, how it can transfer. So we give you this image and we want you to generate someone with a black hair, blonde hair, gender, age, or multiple attributes, multiple domain. You want somebody that has a black hair and different gender, with age, or gender and age, or all of them together. So that's what you see there. And now they also did, when they used just one data set, so they did an experiment on just one data set, but they also claim that their network can work on more than one data set. So this is when they actually use a joint data set, and they discovered that they have even a better, clearer image with multiple data set. So these are their experiments, carry out experiment on Amazon mechanical truck, and for people to be able to rate which image is they actually put like a question. They put an image and they try to put a question that which of the following images correctly classify the image. So they put this output of the other methods as options, and that of StarGAN as options, so that people can say, oh, this image out of the 4 options, I think this option is close to the answer. So, and they discover that 66%, this scores 66% when they post question on air color. This scores 39%, and this scores 70%. So just to show that their method is doing better, even for anonymous evaluation. People that don't know what the intention of the questions were able to always pick the result, the output of StarGAN as the correct answer. So they did the same thing for multi-attributes, and they see that StarGAN actually performed well. So the same thing was also done for another data set, and that is what you see here for the RFD. So that is about all in this paper. I quickly show some appendix, some interesting thing here. This is where it's illustrated when they train the network on multiple data sets. So you can see here that now they introduce a max vector. So the orange represent the cellular data set, the green represent the RFD data set. So what they do is that they have these two data sets during training, but they use this vector to be able to talk the data set. Okay. So when training with real images and training with fake images, so if they put real image, the discriminator is to classify whether it is real, and fake image, the discriminator is to classify it whether it is fake. But if it is a real image, the discriminator will now be able to now say which of the attributes are in that particular real image. So for instance, this is a real image, and if we go through this, so you have one corresponding to brown. So it's saying it has a brown here, and it's saying it is young. So that's what this is saying. For the other data set, this is for another data set. So they put the real image, so it's showing one here, and one corresponds to angle. So it's saying that the real image is actually angle, and you have zeros on the other. So that's what's happening for the two data sets here. So here is considering the cellular A, here is considering the RFD data set. And you have the generator side. So what is happening here is that in the generator, this is a max vector we're talking about. So what this does is when you have one, then that means it's actually referring to the orange. So to pay attention, it will draw sample from the cellular A data set, and when it is one on the other side, it will draw samples from the RFD data set. So now you are putting in an input image into the generator, and you specify the attribute or expression on this. So since this is a cellular A data set, you specify the attribute here. So they are saying that okay, in this input it has they put the input image, they put the data set, and they are saying that okay, we want you to generate an image in this domain. And what is the domain? One is you should have a black hair, two is it should be male, and three is it should be young. And you can see the result here. It is that result they are feeding into the discriminator. Okay, and here the discriminator is full. So the discriminator is considering, is saying this image, this fake image, as real, and is predicting the attribute as black and male and young, which is the intention of the network architecture as it designed as well. So in the training process, while the fake image is generated, we combine the fake image with the original domain label. What is the original domain label? The original domain label is that this actually has a brown hair and it is young. So that information is concatenated with the fake, sent back into the same generator. They just duplicated this for explanation sake, but it's the same generator. It's not two generator network, the same. Then to reconstruct the image, and this goes for a number of iterations until it stabilizes. And after it has stabilizes, then they send the output to the discriminator until the discriminator is able to actually get full. The same thing here in the other data set. The input image and the target domain they want, so they put this image and they want the generator network to produce this image in one at the top to produce an API. So they want to turn this one to API, as you can see here. So when the training has stabilized, they send the generated image into a discriminator, and the discriminator gets full. Okay, this is real, and the discriminator is able to classify it as API. That means it has been actually been full. In the process of training the generator, they repeat the same thing. They take the generated fake image and actually combine it with the original domain label. And what is the original domain label here? It is that the person is angry. This is angry. And they continue with the same generator, not duplicated the same, and to reconstruct the image back until it stabilizes, and they are now able to send it to the discriminator to be full. So this is the network architecture they use. So it contains two parts, the generator part and the discriminator part. Let's look at the generator and discriminator network first. So the discriminator network consists of this number of layers. So it has, so I can say it's a 6-layer network. So it has 5 hidden layers, and it has the output layer for the discriminator source, and output layer for the discriminator classification, and this is the input layer. So the image is colored, so it has 3 channels, and what they did is, after passing it through this conf layer, they use the Adversarial as the activation function, and the number of n, k, the stripe is 2. We define what n is the number of output channel, k is the kernel size, s is the stripe, and what is p. So p is the padding size. So this is the configuration of the input layer. So, and these are the corresponding outputs to the generated 2048. So similar thing we also see there for the generator network. In the generator network, they actually use a receiver block because it's essentially an autoencoder. So first, they can sample the image after and they want to encoder, decoder, and they upsample back the image. So it came in with 64, that is 64, and they bring it back to that, and comes back to the 3 channels. So they use activation map time H here, and they use value rectified hidden unit. What is the in? They use instance normalization vector. So that's essentially this paper. It's an interesting work, and I hope I've been able to contribute to knowledge in understanding this little part of this paper. Oh, thank you for listening. Do subscribe for subsequent um, explanations, and please give us a like. Thank you. See you in the next one.